So first I'll have some opening credits. I'll run through them real quick. I'm going to be talking about a lot of work that I'm doing in collaboration with Elias Pedersen, who's our obstetrician. You'll find out why in a moment, as well as a lot of the work I'm presenting has come out of Britta and Jamie's work. Jakob Anderson has a brief thank you to acknowledge as well. My group focuses on these things. I'll skip past it. So I'll go back and talk about something we do with electrodes called the electroretinogram. It's something that's routine in eye clinics. The textbook electrode looks like that. It's not something you want to do for healthy vision science experiments. And certainly some patients wouldn't like it. You might want to use it for neurological testing, but it's something that also for a neurological patient, maybe it's not the best idea. In our lab, we've been using something that's a little bit more comfortable. It's called a DTL fiber electrode. But it's still not for everyone. It's still something on your eye. It feels like if you're a contact lens wearer, it feels like the very first time you put a contact lens in your eye. Kind of sucks. Those of us who have experience wearing contact lenses, we're okay with it, but there's a lot of people who are left out. Back in Helsinki in the late 70s, early 80s, they were doing experiments out in the woods, in cottages. They discovered they could measure retinal signals with squids when squids were a brand new technology. And they were playing around with what sort of signals they could measure from the body. Give you a recap of what you might expect. It's a little bit like an EEG evoked potential. There's some classic waveforms that you will see when you flash light at someone's eyes. So rather than coming from visual cortex, these evoked responses are coming from the retina. So that's what we've been measuring with electrodes on the eye. They're effectively the responses of the photoreceptors, bipolar cells, and we hope the ganglion cells in the retina. We wanted to see if we could find a more comfortable way to measure these things so we can expand who we can measure. And of course, we thought of OPMs as a rather comfortable alternative to these electrodes on the eye. Long story short, we can find that we get the same waveforms, at least the slower waveforms. The A wave and the B wave are the classic ones they would look for in the eye clinic. These correlate really, really well with what we can measure with an electrode. We did a study that we published and found that just about everybody can have these reproducible waveforms measured with an OPM, not even touching them, just floating over their temple. So we were really, really happy about that. My PhD student, Jamie, he went to Berlin to try to measure this in the PTB, where they have one of the best shielded rooms in the world with something like 8 layers. We wanted to capture the high frequency oscillations from the retina that we couldn't measure in our own ordinary shielded room in Aarhus. And we were in fact able to find them. These are about 140 hertz at their upper limit. And that's compared to the ERG high frequency oscillation that you see here. So the fidelity is still not quite as good as you get with an electrode on the eye, but it's something that at least in ideal measurement circumstances, we were able to capture. And we're hoping that with some signal cleaning, we can take that back to our own ordinary shielded room and measure the same thing. Recently we failed, but we hope to try again and do some more of the signal processing that we've been seeing earlier today. All right, George skipped over this. I'm going to go very quickly over it. This is work that came out of his lab, where they measured the spinal cord evoked responses, or spinal cord evoked responses using OPMs. It was Lydia Mardell dragging that work in Sven Bestman's lab. And they showed this kind of response from the spinal cord. So they were doing median nerve stimulation, so effectively doing strong somatosensory stimulation of the hand. Normally you would look at the brain response in somatosensory cortex. They were hoping to see the signal traveling, like leaving the peripheral nerves of the arm and entering the spinal cord on their way to somatosensory cortex. And it seems that they were successful in doing that. They found this evoked response that they published some time ago. And we wanted to replicate that in our lab. So my student, Jakob, in collaboration with Francesca Fardo over in Aarhus, we were interested in spinal cord measurements for looking at tactile. Later, we want to look at pain responses and things like ALS, neurodegeneration. But we wanted to replicate what Lydia showed in her paper. And it took us a few attempts. And this is an attempt that we did after we tried a few different signal cleaning techniques. The one that Jakob settled on was SSP, which helped us pull out something similar to what Lydia published in her paper. So we're happy that we're able to replicate that, and we want to do some more things with that in the future. All right, so I'll slow down a little bit since this will need a little bit more time. The next thing we're interested in is fetal brain monitoring. Today, ultrasound dominates the monitoring of pregnancy and fetal development. You can see a lot of great things with modern ultrasound. If you haven't had a baby or a friend who's had a baby in the past few years, ultrasound's made great strides in the past decade. You can get movies of your baby in the womb. You can see them yawning. You can get blood flow really well measured. You can look at the brain structure. Now we're getting to detail that's really approaching MRI in terms of brain structure just with ultrasound, but you can't see fetal brain function. So that remains entirely unmonitored. It's a problem in the clinic when the pregnancy is a high-risk pregnancy, or if they know there's a pre-existing condition that they need to follow up on. They can look at things like blood flow and brain size, but they can't really measure what the brain is doing. And that's a big clinical need. Of course, there's a lot of developmental neuroscience questions that also are not completely verified in humans because of this limitation. So just to remind everyone, fetal MEG is a thing that has been done with squids. We're talking about yet another order of magnitude smaller than what we measure in the adult brain. So, one of these easy problems, right? And but magnetometers to measure these things, they're theoretically a no-brainer. The ironic thing is that electrodes cannot measure them because by the time the brain is big enough, the baby forms a waxy layer, and wax is an electrical insulator. So even the bigger signals from the heart actually go away in the third trimester. In the second trimester, the brain's not really big enough to measure much with electrodes on the belly. So magnetometers are really the last resort. And like I said, the fetal MEG is an order of magnitude smaller than adult MEG. And with squids, of course, you couldn't stuff a pregnant belly into an ordinary squid helmet. So there have been a couple custom helmets made to fit pregnant bellies. One of them's in Tübingen, another's in Arkansas. Well, there's only two of them in the world because they were quite expensive to make, and honestly, the cost-benefit ratio wasn't there. The signals were still rather challenging to find in many cases. But when they were successful, they're able to flash lights at a belly and get visual evoked responses like you see here. All right, so OPMs, of course, we were thinking could provide a very convenient and more affordable alternative. The very same OPMs that we're using for all of the experiments that we do in adults on the head, they'll also work for this application, we hope. In Wisconsin, Sarah Strand and Ron Mackay's lab published some of the first demonstrations of measuring the fetal cardiogram compared to squids. And they found actually that in certain situations, the OPMs actually gave them cleaner signals and stronger signals than the squids did. They've been doing a lot of work with the fetal cardiogram over the past few decades. And so they were really, I think, excited to see that they were getting sometimes even better signals with the OPMs. Their trick was they made a custom bed where they could have the volunteer lie down with her belly over the sensors. And so the baby would then be pulled down with gravity and get a little bit closer to the sensors and hopefully not move around too much as well. So with all of that, they got really, really good reproducible fetal cardiograms. They were even able to find some clinical abnormalities in high risk groups with that. And given how clean these are, the signal amplitudes really inspired us to give it a go to find brain signals. First, we wanted to replicate the cardiogram as well. We're not in any way cardiac experts, but right away we found in every single attempt that we made pretty clear fetal cardiograms. This is what this raw signal looks like without any cleaning from OPMs on the belly in the third trimester. You'll see there's big heartbeats here. That's from the mom, even though we're measuring mostly from down here. And the little heartbeats that are faster in between, that's coming from the baby. That's something we can also independently confirm with ultrasound. We know that the heart rates match up. And if we apply something like ICA, then they separate out really nicely. So ICA out of the box will take those signals and spit out the mom's waveform and the fetal waveform really, really nicely. So that's something that we've been able to replicate in several mothers by now. It's robust. Again, once we saw how clean the ICA performed with this, we're like, wow, this is getting really close to what we need for fetal MEG. and we gave that a shot. So at first we tried using the heartbeat itself as a stimulus. That seemed to work. Sorry. Back here. And that was supposed to be a movie, but I guess it didn't transfer over. But in the end, we had a little bit of a physical problem presenting light flashes to pregnant bellies because we were putting OPMs and all the cables in front of the belly and trying to flash light at it at the same time. That's something that we still need to perfect a little bit. So here's one of our first attempts. But in the end, we were able to find, even with that setup, pretty clear evoked responses that match what people were finding with squids with the older squid-based setup. So in the third trimester, you expect 200 millisecond evoked response to light flashes. And that's something that we saw here in our first attempt. We decided to switch to red light flashes since that's what they typically use with the squid-based technique. And found pretty similar results as well. And finally, we decided to spread out the sensors a bit more, allow more light to get into the belly, and with this kind of arrangement. And when we do that, we still get that really lovely 200 millisecond response. With this most recent pilot that we did, we also simulated a rest condition, or we had a rest condition where we pretended like there was light reaching the belly, but we blocked it. And did all the same analysis, hoping to see that there was no evoked response to light not getting to the belly, and in fact that was the case. So processing the data in exactly the same way with light flashes gives us this. When there were no actual light flashes reaching the belly, we get that waveform. So we're pretty convinced that that we're really measuring fetal brain responses and not some other artifact caused by the stimulation. All right, so where we're going with this is going back, and we didn't want to diss ultrasound too much. Ultrasound provides a lot of the ingredients we might need to make this into a sort of holistic technique where we combine the structural imaging we can get from ultrasound with the fetal functional information we can get from OPMs. The ultrasound world has been doing a lot of the work that we need to get sort of source localization going. They can extract the brain, they can segment the ultrasounds really well, they can get eye position even, and these are all the things that we need to know in order to really get source localization like beamforming working with OPM fetal MEG. All right, so just to conclude, OPMs, as you saw from what I've demonstrated and what from George was showing, free MEG from its previous limitations to a large extent. We can expand MEG beyond the adult brain as well. More comfortable measurements of the retina and spinal cord are something we can expect to see. I forgot to mention that in the clinic, if they did a spinal cord measurement, they would often implant into the spinal cord. So again, not really the most comfortable of things to do. And finally, if OPMs really are reproducible with measuring fetal imaging, it's something that we can bring to many more labs and hospitals, and not just the two that remain. So I think anybody with an OPM system would be able to measure fetal MEG in the future if this keeps working. All right, and finally, I'd like to plug, I have some positions available. We're funded to develop fetal OPM MEG even further in collaboration with our ultrasound expert, Anna Nemberete at Oxford University, and Hubert Kreisel at Tübingen, who's been developing fetal spoon MEG for a long time. Thank you for your attention, and I'd like to thank my colleagues and collaborators again.